Avalanches. Across the planet where there is snow, no mountain is safe.
Quand on regarde les images d'avalanche, quand on voit comme ça peut avancer, on conçoit que ça peut effectivement facilement écraser des bâtiments, détruire des murs, exploser des maisons.
Although nothing can withstand these monstrous movements of snow and their paths of destruction, thanks to science, we now understand more about how they work and the power they have.
Une avalanche, pas forcément très importante, peut exercer des pressions de 10 fois la pression équivalente à un cyclone.
Depending on the type of snow they're composed of, the weather and the slope, avalanches can form an enormous cloud of powder that reaches an incredible speed of over 300 kilometers an hour, the speed of a high-speed train. When it is humid, they are slower, but they still exert a force that nothing can withstand.
C'est comme si sur une table qui fait 1 mètre par 1 mètre, vous mettiez 20 éléphants les uns sur les autres.
Faced with these natural disasters, researchers and rescue workers are putting measures in place to predict and limit the impact of avalanches. Scientists have made incredible and surprising discoveries. Forests don't slow down avalanches, rather they make them more destructive. Also, temperature differences of 20 degrees have been measured within 1 mound of snow. These anomalies make the layers of snow particularly unstable and maximize the risk of an avalanche. We're going to show you the amazing mechanisms that science has discovered within these mysterious forces of nature. We're going to follow the story of Xavier Delarue. In 2008, the professional snowboarder and several-time world champion narrowly escaped an avalanche that nobody could have predicted.
J'ai fait plus de 2 km dans l'avalanche, donc c'est un truc de fou, quoi. C'est le genre d'avalanche dont on ne survit pas.
In Italy, we will see that an avalanche can exert an unimaginable force. In January 2017, one of these catastrophes moved a hotel dozens of meters and buried everything that remained.
Allora c'è un lavoro di scavo in superficie della neve, questa coltre di neve è molto alta, raggiunge anche i 5 metri di altezza.
Eventually, we will see that humans sometimes initiate avalanches for self-protection, a high-risk activity that almost cost a professional his life. At the end of the 1980s in France, a man was saved by the snow that should have killed him.
Sortir indemne d'une avalanche ayant été enseveli à plusieurs reprises relève du miracle.
Scientists already know that it's impossible to prevent all avalanches, but might it one day be possible to predict them? Might we soon be able to protect people from their destruction? And what impact will global warming have on these particularly destructive waves of snow? A muffled sound from the mountain, the ground begins to shake. Suddenly, millions of tons of snow are hurtling down the slope. Sometimes it's in a compact wall, and sometimes in a cloud of white smoke. But don't be fooled. Even a few centimeters of snow is enough to carry you.
J'ai des cas d'accidents en alpinisme, en couloir, où la plaque qui part, c'est 3-4 mètres de large, quoi, sur quelques centimètres d'épaisseur, mais ça suffit pour faucher l'alpiniste et puis qu'il se retrouve en bas du couloir.
Where there are mountains, there are avalanches. And although we hear a lot about avalanches in the Alps, they happen all over the world. There are roughly 500 a year, and it's the countries whose mountains are part of the Himalayas that pay the highest price. From Nepal to India to Afghanistan. The statistics from the last century are merciless. This is the country with the highest number of avalanche victims. Here they are responsible for 828 deaths, some as the result of huge catastrophes. The altitude is of course one cause, but that's not the only reason. Many people live scattered in places that are very difficult to access, and the prevention and rescue infrastructure is limited. The second most affected mountain range is in Europe. the Alps. On the 23rd of February 1999, a ski resort in Austria fell victim to an avalanche so enormous that it was nicknamed the Alpine Tsunami. 170,000 tons of snow covered the resort, carrying 40 people. In France, avalanches are responsible for an average of 30 deaths per year. It's the second most visited country in the world for its ski slopes. Unfortunately, accidents do happen, but researchers are working to ensure that previous catastrophes aren't repeated. Today, thanks to science, specialists know a lot more about this catastrophic phenomenon and what triggers it. But what is an avalanche exactly?
Une avalanche de neige, c'est l'écoulement d'une masse de neige le long d'une pente. Le facteur principal, c'est la gravité. Il faut une pente et de la neige.
The main ingredient, of course, is the snow that forms in the clouds when they reach a certain altitude and state of solidity. A phenomenon well known to scientists that unfolds in stages. Firstly, there are the clouds. Clouds consist of water vapor, that is, water in the form of a gas. Yet, contrary to what we might believe, water molecules are lighter than air, so when they form clouds, those clouds rise in the sky. And the higher they rise, the colder they get. So the water vapor that forms the clouds undergoes a transformation thanks to a physical phenomenon, condensation.
La condensation, c'est le passage de la matière de l'état gazeux à un état que l'on appelle condensé, c'est-à-dire soit liquide, soit solide. Dans l'atmosphère qui nous entoure, il y a la présence d'eau sous forme de gaz, on appelle ça de la vapeur d'eau. Et quand cette atmosphère se refroidit, cette vapeur d'eau va pouvoir passer de l'état gazeux à l'état liquide, ça donne de la pluie, ou de l'état gazeux à l'état solide, ça donne de la grêle ou de la neige.
As it gets colder, the water vapor becomes liquid, and if the temperature falls below 0 degrees, the water freezes. Yet we still don't quite have snow. When the water freezes, it forms tiny crystals. But in order to become snowflakes, those crystals have to attach themselves to one another around a small particle, usually a particle of dust, sand, or ash. Thanks to this fixation point, the crystals attach themselves to one another whilst leaving spaces in between. That's how they form snow and not ice.
Donc les deux constituants de base, c'est des grains de glace, si on peut dire, et de l'air. C'est-à-dire qu'en fait, c'est un matériau poreux, c'est un peu comme une éponge. L'éponge, c'est de l'éponge et de l'air, et là, c'est pour la neige, c'est de la glace et de l'air.
The snowflakes are born. As soon as they're heavy enough, they will fall from the clouds. And it's when they cover the mountain peaks by the billion that these innocent little flakes become a death trap. It's on the mountain peaks where there is the most snow, but in high altitude we are closer to the sun than to sea level. How can this be explained? The answer is surprising. It's not the sun that warms the air, or at least not directly.
Les rayons du soleil ne réchauffent pas l'air, mais réchauffent le sol, et c'est après le sol qui réchauffe l'air.
The sun's rays have to bounce off the ground to heat the atmosphere. So the further from the ground you are, the colder it gets. This explains the average temperature at the Everest summit. It's minus 42 degrees centigrade at 8,848 meters. That's why there's a lot of snow on the mountains. There's also another characteristic of mountains that makes them a breeding ground for avalanches: steep slopes.
À partir donc de 30 degrés, 28-30 degrés, là, il faut être particulièrement vigilant.
According to research, the majority of avalanches are triggered on slopes between 30 and 45 degrees. And it's this kind of terrain that's particularly attractive to free riders, who prefer slopes that are off the beaten track.
Le gros en fait de l'accidentologie concerne les skieurs de randonnée, donc la randonnée à ski, et les skieurs hors piste, alors skieurs ou snowboarders. C'est plus de 80% des accidents d'avalanche.
And it was when he was far off-piste that champion Xavier Delarue fell victim to an avalanche that he triggered on the 29th of March 2008.
J'ai vu autour de moi tout le manteau neigeux qui a commencé à se fissurer. Donc en gros, partout où je regardais, je voyais tout qui partait en gros morceaux. Je me suis dit, waouh, là je suis vraiment dans la mouise.
The avalanche that carried Xavier was several hundred meters wide and traveled 2 kilometers. That's at least 20,000 tons of snow, 2 times the weight of the Eiffel Tower. It's a miracle that Xavier is alive today.
C'est un truc de fou, quoi. Enfin, voilà, c'est le genre d'avalanche dont on ne survit pas.
So how does a harmless snowflake falling from the sky turn into a cold murderer? Well, it all depends on what happens when the snow accumulates on the ground, forming what scientists call the snowpack.
Le manteau neigeux, ce sont les différentes couches de neige qui vont s'accumuler tout au long de l'hiver. Il va neiger, ça va former une première couche de neige et tout au long de l'hiver, ça va continuer et la couche de neige qui est déposée au sol va s'épaissir.
With each snowfall, a new layer is formed. The snowpack is effectively a millefeuille, comprised of layers of different types of snow, and it's this difference that causes the avalanche. But why are the types of snow different?
On pourrait se dire, la glace c'est dur, ça ne va pas bouger s'il fait pas en dessous de 0 degré, s'il fait froid. Mais en fait, pas du tout. Ces cristaux ils vont constamment se transformer durant tout l'hiver.
The first cause for the changes to the crystals is the wind. This carries off the very light snowflakes and breaks them into small grains. Then comes the second cause, the temperature in the snowpack. It's this that determines whether the snow will become a layer that poses no danger to the skiers or whether it will become the foundation for a terrible avalanche. Option 1, the temperature is sub-zero throughout the snowpack. The broken snowflakes are in the form of small grains and have lots of surfaces, allowing them to attach themselves to one another.
On va vers ce qu'on appelle des grains fins, des tout petits grains qui sont soudés les uns aux autres. C'est de la neige sèche, il n'y a pas d'eau liquide et il y a un petit pont de glace qui se forme entre les deux grains. Et donc on a un manteau neigeux avec une structure plutôt solide.
The grains that have been rounded by the breaking force knit themselves together until a tight layer is formed. The risk of an avalanche has been reduced. Option 2. The temperature between the bottom and the top of the snowpack is very different, because contrary to what we might think, it's warmer underneath the snow than above it.
La neige, on le sait également, est un matériau isolant. Quand on se perd en montagne, qu'est-ce qu'il faut faire? On fait un igloo pour se protéger et pour pouvoir se réchauffer. Et bien là, il va se passer la même chose.
The insulating quality of the snow and also the heat coming from the center of the earth keeps the lowest layers of snow warm. On the other hand, the snow at the surface can get to minus 20 degrees during the night or if there's wind, because there is nothing protecting it from the cold.
La neige qui est à la surface, en fait, elle rayonne énormément. Elle perd beaucoup d'énergie. C'est comme si vous sortiez sans vêtements ou en t-shirt en plein hiver. Vous sentez que vous perdez toutes vos calories. Et là, c'est pareil, la neige qui est en surface, elle perd toutes ses calories.
0 to 1 degrees at the bottom, minus 20 degrees at the surface. This wide range in temperature is what causes a change in the water molecules that make up the snow. It's what the physicists call sublimation.
Alors le processus de sublimation, c'est simplement l'évaporation des molécules d'H2O, d'eau, mais qui sont sous forme de glace. C'est-à-dire c'est la glace qui s'évapore et qui devient vapeur d'eau.
Because of the heat of the Earth, the water molecules in the deepest snow move from a solid state to a gaseous state, water vapor, without going through the liquid phase. This vapor rises, and because the snow on top is a lot colder, the vapor refreezes, condenses, and settles on the grains of snow that are already there.
Le grain au-dessus va grossir sous forme pyramidale, et deux grains de ce type-là ne sont jamais solidarisés entre eux. Il n'y a pas de petits ponts de glace, et donc ça fait comme des petites billes, et c'est un manteau neigeux très instable.
When there is a difference in temperature, the grains at the top of the layer get bigger. There are therefore fewer of them, and the fewer there are, the fewer points of contact are available. Scientists refer to the biggest ones as depth hoar crystals, and they are particularly dangerous.
Si on prend une couche de neige de gobelet, on essaye d'en faire une boule de neige, ça ne marche pas. Et donc du coup, quand il neige par-dessus, comme ils ne se tiennent déjà pas entre eux, ils n'arrivent pas non plus à tenir la neige qui va les surcharger. Et donc c'est eux qui font le rôle de couche fragile, le rôle de roulement à billes, si on veut.
The required conditions for an avalanche have been fulfilled. The snow layer has become very fragile. All it takes is a new layer to settle on top and the trap is ready to close. And that's exactly what happened to Xavier Delarue. It was in the Alps that the snowboarder nearly lost his life at the beginning of 2008. It happened more precisely in Switzerland, around 50 kilometers to the northeast of Mont Blanc, on the north face of a summit called Châtelet.
On avait fait une première journée où tout s'était quand même super bien passé. On a eu des conditions stables, on n'avait rien qui avait bougé. C'était plutôt idéal.
In the early afternoon, the weather was lovely. The sun was beaming over the summit of the snowy peak. Xavier got ready to ride off-piste, far from the beaten track. It's normal for him, it's his job. A whole team rallied around him for the event.
L'hélicoptère est là, il est équipé, il a tout ce qu'il faut. Dans le contexte, il y a tout ce qu'il faut si jamais il y a un accident. Mais bon, ça n'empêchera pas l'Avalanche de partir.
Exhilarated as he was by the good conditions, Xavier was about to make a monumental error.
J'ai vu cette pente sur le côté qui avait une belle lumière qui me paraissait bien. Et je me suis dit, allez, il faut qu'on aille faire cette dernière vite fait. Elle est facile, donc pas besoin de prendre notre procédure pour l'analyser, etc. On y va.
Yet to specialists, the way the snow was resting on the peak suggested that there had been a lot of wind. And wind is one of the Avalanche's best friends.
Le transport de vent, c'est quelque chose d'extraordinaire qui, en quelques heures, peut vous changer complètement la physionomie d'un terrain.
The top layer of snow transformed into a layer that had no cohesion, a real rolling carpet made up of millions of tiny beads. If a new, denser layer was to form on top, an avalanche could be triggered at any moment. And usually, it's the wind that is responsible for forming this new layer.
C'est-à-dire que le vent a une capacité, à partir d'une certaine vitesse, en fonction du type de neige, du type de grain de neige, à transporter une grosse quantité de neige et la redistribuer, la porter sur une zone particulière. Le vent peut très bien doubler, tripler la quantité de neige sur une zone de départ particulière par rapport à la chute de neige initiale.
Wind can easily cause a huge quantity of snow to build up, but that's not all. It also changes the snowflakes, breaking them into small grains. The stronger the wind, the smaller the grains become. As scientists have determined, the smaller the grains, the more they will knit together. The new layer will therefore have stronger cohesion and form a slab. If the cohesion is very strong, you have what scientists call a wind slab. In an avalanche, these are easily identifiable because they move in blocks. With a medium cohesion level, it is a soft slab. These are perhaps the most dangerous for skiers because they are unidentifiable until they move.
Le problème des plaques friables, c'est qu'on ne peut pas les détecter. Parce que les plaques friables, ça a l'apparence de poudreuse, mais ça se comporte comme une plaque parce qu'il y a quand même de la cohésion suffisante pour que s'il y a un effondrement de la couche phréatique qui est en dessous et qu'elle s'est propagée, eh ben, il y ait une masse de neige suffisamment étendue horizontalement pour que ça soit non pas ponctuellement quelques mètres carrés qui partent en avalanche, mais plusieurs dizaines, voire plusieurs centaines de mètres carrés.
This is exactly what happened to the snowboarder.
Il y a une première poche qui est partie qui m'a vachement surpris. Donc c'était une plaque d'à peu près une vingtaine de mètres de diamètre.
Xavier had barely begun his descent when the wall of snow beneath him came loose. All it took was Xavier's 80 kilos plus his kit. How did that happen? When he passed over the soft slab, Xavier exerted a force on the mountain over a very small surface. The size of the snowboard, less than 1 square meter, you might think that the smaller the surface, the lesser the risk. In fact, it's the opposite.
Le poids d'un skieur, ponctuellement, sur une surface faible, peut déclencher une avalanche, alors qu'une chute de neige importante sur toute une surface ne va pas déclencher l'avalanche. Au même endroit, le skieur va la déclencher. C'est une histoire de contrainte, en fait. C'est qu'il va exercer une force équivalente, mais sur une surface beaucoup plus réduite.
The force exerted by Xavier's weight was concentrated and therefore multiplied. It penetrated the snowpack and reached the fragile layer. The fragile layer was destabilized and the soft slab on top cracked. A whole section fell away, taking the snowboarder with it.
Soudainement, la plaque, elle n'a plus son accroche dessous elle. Donc qu'est-ce qui se passe? Eh ben, elle essaye de s'accrocher autour d'elle, donc ancrage aux ancrages latéraux et à la neige qui est au-dessus. Donc elle va tirer très fort sur le reste du manteau neigeux. Cette traction va devenir trop forte pour la neige qui est tout en haut et une rupture va se produire à l'endroit le plus faible. Et cette rupture locale, un peu comme une fermeture éclair que vous ouvrez, eh ben, elle va se propager.
The slab came loose. It didn't look enormous, less than 20 square meters. As an extreme mountain sports professional, Xavier wasn't worried at first. He felt he could outrun the falling snow. But that would be quite a mean feat. Soft packs are composed of snow that is quite light, so they slide very quickly.
Quand même une petite plaque part, c'est quand même déjà du poids. C'est de la vitesse, ça va très vite. Hein. Une avalanche de plaques, vous pouvez avoir des vitesses de l'ordre de 200 km/h.
Thankfully, the small plaque, composed as it was of humid snow, went a lot slower. But suddenly, another enormous slab came loose. Everything started to move.
Toute cette pente du haut, donc, qui a quand même amassé pas mal de neige tout au long de la pente, est arrivée sur la pente du bas et a mis énormément de pression et a déclenché toute la pente.
The second slab spanned the width of the slope. Nothing could resist it. This slab wasn't triggered directly by Xavier, but by the first slab.
Vous avez une espèce d'enchaînement en cascade. Chaque petite avalanche ou moyenne avalanche, par la surcharge qu'elle crée quand elle se met en mouvement, va faire un effondrement qui va en déclencher une autre, dont l'écoulement va lui-même faire une surcharge qui va en déclencher une autre à côté, etc.
As often happens, there wasn't one but several avalanches at the same time. For Xavier, there was no way out. The snowboarder disappeared out of the video, buried in a flurry of snow.
Quand on imagine, quand on se fait prendre par des vagues à l'océan, quand on prend une grosse vague, on voit ce que ça fait. Là, il faut imaginer, c'est 2, 3, 10 vagues à la suite, hein, dans un grand toboggan parfois.
Et je me rappelle de me faire vraiment secouer comme une puce. Un coup, 2 coups, 3 coups, après je suis tombé inconscient.
The avalanche was enormous. It traveled more than 2 kilometers.
La cassure faisait plus de 100 mètres de large sur 2 mètres de haut, donc c'est des quantités de neige invraisemblables.
For the team in the helicopter, it was impossible to distinguish anything among the millions of tons of snow that had been dislodged across such a large surface. It was a miracle that Xavier was found alive at the bottom of the slope.
J'ai fini dans une vallée en bas où toute la neige s'accumule, où normalement on finit sous des mètres et des mètres de neige et jamais on vous retrouve jusqu'au printemps.
It was whilst coming down the slope that a skier from the team found Xavier lodged in the snow, almost unharmed. Normally, avalanches bury you bit by bit. This is nearly always the case for skiers, and the risk is even greater for snowboarders.
Le pire, c'est de se retrouver en snowboard dans une avalanche.
Du moment où la neige, vous êtes chopé par la neige va appuyer sur le snow et ça fait ancre. Comme on dit, ça fait ancre, ça a tendance à vous tirer vers le fond.
During an avalanche, the snow puts pressure on all possible surfaces, and the surface of a snowboard is much larger than that of a pair of skis. Specialists reckon that the pressure exerted can be up to 3 tons, as if a full minivan were to push down on the board. So why was Xavier not pulled down into the snow? Thanks to a special rucksack, an airbag rucksack.
Lorsqu'on est pris dans une avalanche, c'est un sac à dos dans lequel on a une réserve d'air avec des coussins qui, lorsqu'on actionne cette réserve d'air, ce sont des coussins qui se gonflent et qui vous permettent d'être maintenus en surface.
Being full of air, the airbag rucksack stops the victim from sinking down into the snow. To help you understand, here's an example of an accident survived by ski freeriding champion Ima Navarro. When a whole wall of snow came loose in one enormous slab, Ima tried to ski on the moving snow.
Ya llegó un momento que había un cliff de 2 o 3 metros, que entonces ya es cuando toda la avalancha por detrás me cogió y ya me empezó a revolcar.
Like Xavier, Ima disappeared into the clouds of snow suspended in the air, but he managed to stay at the surface and was found a few minutes later. The inflatable bag is there for good reason, but specialists agree that even equipped with this technology, Xavier was incredibly lucky.
Sortir indemne d'une avalanche, avoir été emporté sur un long trajet, ayant été enseveli à plusieurs reprises, relève du miracle.
Xavier was indeed very lucky to survive such a huge avalanche. However, contrary to popular belief, it's not the quantity of snow that makes an avalanche likely. In fact, it's the opposite when it comes to the thickness of the snowpack. Because if you remember, for an avalanche to be triggered, there must be a big difference in temperature between the top and bottom layers of snow.
Si vous avez 10 degrés de différence de température entre la surface et la base avec un manteau neigeux de 2 mètres, bon, ça ne fait pas une grosse variation quand vous descendez. Par contre, si c'est 10 degrés de différence, vous les avez sur 50 cm, vous réalisez que ça fait une grosse différence. La température varie fortement dès que vous descendez un petit peu dans le manteau neigeux.
This big difference accentuates the instability of the snowpack. But for an avalanche to start, it needs to be triggered. And it's nearly always a human that does this.
Nous avons des avalanches de plaques, et là c'est 90% donc qui est fait par un déclenchement qui est fait par l'homme.
Only 10% of avalanches are triggered by natural causes, and most of the time in places where people aren't affected. However, these natural occurrences can take victims too. On the 23rd of September 2012 in Nepal, 6,800 meters high and in the middle of the night, a huge avalanche descended on a mountaineering camp.
It's like an earthquake, it's like a tsunami, it's an avalanche, and especially an avalanche in the Himalaya. It's the biggest thing you've ever seen, you know.
9 died, including 4 French people. More recently in Italy, and more precisely in the Apennines mountain range in the Abruzzo region, a huge avalanche hit. It was on the 18th of January 2017. The death toll was high. 29 dead, all trapped in a hotel that was completely buried and partly flattened.
Gran parte della struttura era crollata e soprattutto la parte a monte, quindi la zona notte, la cucina, la hall, le legnaie erano interamente sepolte dalla neve e avevano ceduto quindi strutturalmente.
The avalanche was so violent that the building was carried dozens of meters. So what exactly happened? The inquiry is still ongoing, but science has given us some answers as to why the shock was so powerful. First of all, there's the context. In the second half of January, the region was completely covered in snow. Between 1 and 1.5 meters of snow fell in just 24 hours.
Donc c'est des chutes de neige importantes, mais pas forcément extrêmes pour la région.
Another essential ingredient for an avalanche, the slope. The avalanche started near to the summit of Mount Ciela, with a slope of between 30 and 35 degrees. After this gradient, the risk of an avalanche is high, but that still doesn't explain why the avalanche was triggered. Scientists are wondering, what triggered the avalanche?
Il y a beaucoup de questions en débat autour de cette avalanche et son mode de déclenchement, parce qu'au moment où s'est produit l'avalanche, on était dans une période de forte activité sismique.
On the same day, a 5.7 magnitude earthquake shook most of Italy. Its epicenter was at Montereal, a small village 150 kilometers northeast of Rome and around 100 kilometers from the site of the avalanche. Are the two disasters linked?
Il existe déjà des travaux de recherche sur le déclenchement des avalanches par les tremblements de terre. Je dirais que un pays comme le Japon est soumis à ce problème.
It might just be an unsettling coincidence, and there's one factor that suggests that's all it is. The factor is timing. The earthquake took place shortly before midday and the avalanche at 5 p.m. This time lapse doesn't correspond with scientific knowledge.
Tous les modèles de déclenchement des avalanches sont indépendants du temps. Il n'y a pas d'effet du temps. C'est-à-dire qu'on suppose que quand la surcharge arrive, c'est instantané. L'avalanche part tout de suite.
Ultimately, the snow that had fallen over the previous few weeks, even if it hadn't fallen in exceptional amounts, could have created an unstable snowpack that was able to fall as an avalanche at the smallest exertion of force. Finally, what kind of surface did the snow accumulate on? Rocky slopes, or ones covered in forestry or grass? Terrain also plays a role in the movement of an avalanche.
Une pente herbeuse avec de grandes herbes qui se couchent à la première couche de neige, c'est facilement compréhensible que ça fait un plan de glissement. Si l'herbe est pâturée, ça fait des petites aspérités dans lesquelles la neige va venir s'accrocher. Au niveau des rochers, c'est pareil. La neige va venir s'accrocher sur les bords, contre les rochers.
So there you have the different theories as to the causes of the Italian avalanche of January 2017. We remain uncertain as to how a natural disaster of this kind was powerful enough to carry a hotel for several dozens of meters. In order to answer this question, scientists are investigating the destructive capacity of the phenomenon. It's a question of physics. The damage that a building might undergo depends on the pressure with which the avalanche strikes its structure. The pressure might be enormous. Scientists measure it in kPa, kilopascal. 1 kPa equates to 100 kilos over 1 square meter. Even medium-sized avalanches are enormously powerful.
Une avalanche, par exemple, pas forcément très importante, peut exercer des pressions de 30 kilopascales. Donc à peu près 10 fois la pression de 3 kilopascales qui est équivalente à un cyclone de 250 km/h.
The pressure scale for an avalanche can be summarized as follows. An avalanche that exerts a pressure of 1 kilopascal can break a glass. One that exerts a pressure of 30 kilopascal can destroy a wooden structure. One that exerts a pressure of 100 kilopascal can uproot a large tree. And one that exerts a pressure of 1,000 kilopascal can destroy reinforced concrete. 1,000 kilopascals, that's almost 400 times the pressure of a cyclone. It seems huge, yet such a force has been recorded before in an avalanche.
Il faut imaginer, c'est comme si sur une table qui fait 1 mètre par 1 mètre, vous mettiez 20 éléphants les uns sur les autres.
So now we understand how an avalanche was able to move a building like the Italian hotel several dozens of meters. On the 18th of January 2017, all it took was a few seconds for the avalanche to destroy and bury the building.
Questa polvere di neve è molto alta, raggiunge anche i 5 metri di altezza, per cui bisogna inizialmente creare una sorta di, vogliamo chiamarla così, tromba dell'ascensore per capire le dimensioni.
The pressure exerted on the Italian hotel was what scientists refer to as impact pressure, and it depends on two things: the speed at which the snow is traveling and its volumetric mass, i.e. its density.
La masse volumique de la neige, c'est son poids. Sur 1 mètre cube de neige, on va peser la neige et on va donc connaître sa masse volumique.
The density of snow is very different depending on whether it's wet or dry. It can vary between 100 and 600 kilograms per cubic meter. For a given level of damage, the faster the snow is traveling, the less it weighs, and it's on this point that scientists distinguish between different types of avalanche, elaborating on their hypotheses. The first type is an aerosol avalanche, which happens when dry snowflakes are suspended in the air.
C'est comme un grand nuage qui se propagerait le long de la pente, qui va grossir en se propageant s'il y a suffisamment de neige.
Particles of snow flying through the air might seem like nothing, but in fact it can be extremely dangerous.
Ça a une grande puissance de destruction, l'effet de souffle de l'aérosol, qui peut être capable d'emporter des arbres, comme c'était le cas par exemple en Maroc en février 1999.
The Italian hotel was perhaps destroyed by a phenomenon similar to that which destroyed the Montroc hamlet in France on the night of the 9th of February 1999. That time, an enormous snow cloud destroyed 14 chalets, killing 12 people. How can aerosol snow be responsible for such a high death toll? Essentially, it was because of its speed. Traveling at more than 300 kilometers an hour, it was explosive.
L'avalanche pousse devant elle la masse d'air, puisqu'elle descend très très vite. Et donc c'est cette masse d'air qui est poussée à vive allure qui est très destructrice. Et là, c'est en l'occurrence beaucoup moins la neige qui est destructrice, c'est plutôt l'onde de choc créée par la masse de neige qui s'est mise en mouvement.
In the case of aerosols, the snow is very dry and weighs practically nothing. It's the displacement of air, the shock wave, that does the damage. Or rather, the almost instantaneous stop it comes to when it collides with a building.
Une caractéristique de l'avalanche aérosol, c'est qu'elle va très vite. Donc quand elle va impacter un ouvrage, on va demander à l'avalanche tout d'un coup de passer de 300 km/h à 0 à l'impact avec l'ouvrage.
So that's the first hypothesis surrounding the nature of the avalanche that struck the Italian hotel. The second hypothesis is an avalanche of dense snow. This is what we saw with the examples involving the free-riding champions. In this type of avalanche, the snowpack slides the length of the rock face in the form of slabs of differing size. The flow of humid snow is destructive because of its weight. Furthermore, it continues to exert a pressure force until the end of the avalanche, with the snow accumulating on top of the building. The final hypothesis is the most destructive of the three. It combines the aerosol and heavy snow hypotheses and the destructive powers of each.
Et donc là, on serait quelque chose en termes de dégâts qui serait intermédiaire entre l'avalanche d'eau poudreuse qui déplace des bâtiments, qui les arrache par l'effet de souffle, et les avalanches de neige humide qui sont encore plus denses, qui sont beaucoup plus denses, plus lentes, mais qui sont capables également de déplacer, détruire des bâtiments, parce que bien que la vitesse soit modérée, elles ont une telle masse, une telle densité qu'elles travaillent comme un bulldozer, elles poussent tout ce qui est devant eux.
These are the different hypotheses to explain the violence of the avalanche that carried the Italian hotel. And that's not all. The avalanche, already pretty powerful, can gain in destructive power thanks to the materials it pulls with it on its way.
Une avalanche, donc selon sa force, clairement, elle peut effectivement couper les arbres, les arracher, elle peut emmener effectivement des rochers s'il y en a, ça c'est une possibilité. Mais en plus des arbres qui arrivent dans l'avalanche, c'est quelque chose qui va éventrer facilement un bâtiment.
Contrary to popular belief, forests don't hinder avalanches. Instead, as was the case for the Italian avalanche, it makes them more destructive. Speed, mass and transporting everything in their paths, the snow streams seem impossible to stop. On the slopes of Monsila, in the Abruzzo region of Italy, it was after a 700-metre journey that the avalanche hit the hotel. According to initial studies, the hotel structure was hit by 50,000 tons of snow and trees, travelling at a speed of 100 kilometres an hour. Under the force of the impact, part of the hotel collapsed, and the rest was moved several dozens of metres. When the avalanche ended, the whole building was buried under 5 metres of compacted snow.
Quando è arrivata la valanga noi ci siamo ritrovati col soffitto a 50 cm dalla testa e intorno, dietro, ma sotto un vetro ci stava il ghiaccio, eppure diciamo in un buco però un po' più avanti, cioè mi dovevo sforzare a prenderlo, mi dovevo allungare proprio la mano.
Of the 40 people present, 2 were outside at the moment disaster struck, and they managed to call the emergency services. But the weather conditions and the enormous quantity of snow prevented the rescue vehicles from arriving immediately. It was only the following day that 200 rescue workers arrived on site. Work commenced, but the conditions made it very difficult. Inside, the survivors had been trapped in the cold and dark for almost 24 hours. Luckily, the fact that they were in a building increased their chance of survival.
Noi diciamo in valanga lavoriamo spesso e tempi così lunghi di sopravvivenza non li abbiamo trovati quasi mai, però le condizioni sono completamente diverse dalla classica valanga. Ci sono sacche d'aria sotto, per cui diciamo la coltre di neve è altissima, però ha lasciato dei piccoli spazi vitali per le persone.
Lack of oxygen is responsible for 80% of deaths in an avalanche. It's what scientists call hypoxia. Buried in the snow, it's almost impossible to breathe unless there is a pocket of air. And this quickly becomes life-threatening.
En absence de poche, l'hypoxie arrive de façon très rapide. Les lésions cérébrales s'installent très rapidement en absence d'oxygène. C'est une question de minutes. En 30-40 minutes, on aboutit à l'arrêt cardiaque.
In the hotel, there were a number of corners not packed full of snow, and this allowed the few avalanche survivors to breathe. In the end, the death toll was high. Of the 40 people present, only 11 were saved. The building's ruins had prevented them from being flattened or developing hypoxia. Whether it's free riders far off-piste or holidaymakers in buildings, avalanches take no prisoners.
Quand on regarde les images d'avalanche, quand on voit comme ça peut avancer, les masses qui en mouvement plus ou moins rapide, on conçoit que ça peut effectivement facilement écraser des bâtiments, détruire des murs, exploser des maisons.
There are, however, certain areas in the mountains where avalanches are now very rare. Ski resorts. Ski resorts are home to only 10% of recorded avalanches. Ski areas benefit from prevention strategies put in place by scientists. These exist in 2 categories. The first is passive prevention. This involves attempting to stop the avalanches from being triggered.
On va chercher à lutter contre l'avalanche en empêchant son départ dans la zone de départ des avalanches par des ouvrages qui vont retenir le manteau neigeux. Donc on utilise des râteliers, des clés, des filets par avalanche qui vont retenir le manteau neigeux et l'empêcher de partir.
The second type of prevention is active prevention. This involves voluntarily triggering avalanches with explosives in areas where they are likely to happen. In order to determine the zones and the risks, scientists use avalanche history. They measure the snowpack daily to determine its instability. And when the risk is too great, the dangerous avalanches must be triggered before the piste is opened. In places where there is risk year in, year out, the mountains are fitted with permanent systems so that an avalanche can be triggered remotely. This is to limit the risk for the professionals responsible for triggering the avalanche.
Quand on va déclencher, on se déplace forcément puisqu'on va faire des déclenchements dans un milieu qui est instable avec tous les risques liés aux avalanches parce qu'eux-mêmes peuvent partir dans une avalanche.
Trouble is, not all zones are fitted with remote triggering systems. The ski rescuers therefore have to go and trigger the avalanche themselves.
On va jeter de la dynamite, un produit explosif qui va exploser le plus possible en surface du manteau neigeux pour le fragiliser. C'est pas toujours facile, hein.
It's not always easy, and it can be dangerous. Luke Nicolino knows a bit about it. Today's Director of Safety for the La Plagne slopes was once caught in an avalanche. It was at the end of the 1980s, during his days as a tracker. He was working in a zone that he knew particularly well.
Il n'a pas été skié toute la semaine d'avant. Et puis c'est pour moi parce que je suis passé à l'endroit où il y avait une zone fragile, où il y a peut-être eu un écart aussi de température avec les jours précédents.
The slope in question is in La Plagne, on the side of the Bellecote summit. The zone is almost flat and sits above a 20-meter rocky ledge looking over a piste.
Il faisait beau et on avait programmé cette ouverture de ce secteur excentré, éventuellement le lendemain. Et puis comme tout s'est très très bien passé, que dans une grande décontraction, dans une grande euphorie, on a passé un coup de radio, on a appelé tout le monde, on a dit on se retrouve, on va y aller tout de suite.
The conditions were so good that to save time, Jean-Louis and his team decided to operate without explosives.
Ce jour-là, au lieu de tirer couloir par couloir avec des explosifs, on a déclenché à ski, découpé. En fait, quand on passe à ski au sommet du couloir, on découpe le manteau neigeux et ça provoque une avalanche.
We saw this in the example with Xavier Delarue. When the snowpack is composed of several heterogeneous layers, the force exerted by a person passing over sets the fragile layer in motion. This layer, which is composed of millions of tiny bits, triggers movement of the top layer, which is a more cohesive slab. For the trackers, it is a delicate exercise. They are required to pass over the exact point at which the avalanche can be triggered without being caught up in it. It seems dangerous, but at the time the activity was common.
Il restait 2 côtés à traiter. Et on se voit parce que c'est une espèce de cirque. On se voit, moi j'étais de l'autre côté, je surveillais. On se surveille tout le temps comme ça. Quand on fait ce genre de travail, on regarde ce qui arrive aux autres, ce qui arrive pas aux autres.
Je m'arrête pour que mon collègue me rejoigne. Et tout d'un coup, je vois toute la pente se fendre au-dessus de moi, une centaine de mètres au-dessus de moi, sur toute la largeur. Et puis à un moment, il y a tout qui part.
Incredible, the avalanche didn't begin where Luke was standing, but above him. How is that possible? Essentially, it's because of the slab above the fragile layer. If the cohesion is great enough, it cannot crack where the skier is, i.e. where the pressure is greatest. Instead, it transmits this pressure in a wave.
C'est-à-dire que le surpoids, la surcharge qu'on va mettre à un endroit, cette plaque cohésive, peut se propager jusqu'à un point où on va trouver une zone beaucoup plus fragile que la zone qu'on a sous nos pieds.
Scientists call these zones extra fragile, and if they occur meters above a person, it's almost impossible to avoid an avalanche, as Luke was to find out. And the worst thing of all, just below Luke were a number of rocky ledges.
Luc a donc été entraîné très vite dans ces petites barres rocheuses, passé sur un couloir, on aurait dit un gymnaste qui fait du tumbling. C'était la tête, les pieds, la tête, les pieds, la tête, les pieds.
In these sorts of circumstances, avalanche victims rarely emerge alive, and if they do, they normally have extremely serious injuries.
Les victimes des avalanches sont emportées par leur coulée, sautent des barres rocheuses, parcourent des grandes distances, sont littéralement malaxées dans ces coulées de neige. Il y a des phénomènes de compression par des gros blocs de glace.
Luke's journey ended several hundred meters from where he started. Miraculously, his only injury was a sprain to the knee. So how did he survive being thrown 20 meters over a rocky ledge the height of a 7-story building? In fact, it was the deadly snow itself that saved him.
La
La neige étant un mélange de glace et d'air, eh ben, ça fait un bon amortisseur, un gros matelas donc qui amortit ce choc dans la pente une fois la barre rocheuse sautée.
Snow is composed of air and water in solid form. That's what makes it springy, like a sponge. This material absorbs a lot of the impact.
La décélération, pour passer de votre vitesse de chute, 100 km/h ou plus, à 0, comme elle se fait sur 1 mètre de distance, eh ben, ça fait une décélération moins forte et ça, le corps humain est capable de la supporter.
Saved by the quantity of snow, Luke had several strokes of luck. At the end of the avalanche, he was only partly submerged.
Quand on est pris dans l'avalanche, c'est un coup dessus, un coup dessous, et on ne sait plus très bien où on se situe. Et la grande chance de Luc, c'est qu'au moment de l'arrêt d'avalanche, il avait la tête qui était à l'air libre.
Of course, having your head above the surface of the snow allows you to breathe. But even in these conditions, injuries can be serious due to the pressure of the snow.
Quand la masse de neige s'arrête, en quelques dizaines de secondes, la neige prend vraiment comme un plâtre ou comme un gel instantané. Et là, vous êtes prisonnier, comme emmuré. Et impossible de bouger, même le petit doigt.
As we have seen, an avalanche doesn't just stop instantly. When the victim comes to a halt, the snow following behind continues to push down, compressing the snowpack and making it very compact. Luckily for Luke, on that day the pressure of the snow wasn't too high, and his colleagues were able to get him out in a few moments. The prevention and safety organisation put in place in France has considerably reduced the risk of avalanche, particularly on ski resort pistes. The number of deaths by avalanche has stayed around 30 per year since the 1980s, even though there are many more skiers. The preventative and safety measures seem to be paying off. This is a success, but we mustn't forget the dangers still associated with mountains.
Tant qu'il y aura de la pente, de la neige, il y aura des avalanches. Il y aura des avalanches, il faut en être conscient. Et lorsqu'on a oublié ça, eh bien, là, ça devient très dangereux.
Avalanches. They can reach the speed of a high-speed train and the power of a bulldozer in the form of powder, or as a stream so dense you might call it white lava. They're dangerous for skiers and buildings alike. Thanks to science, nowadays we are more able to protect ourselves against avalanches. Specialists have put systems in place to stop them from starting, or conversely to trigger them before they become a threat. But despite these methods, a method of preventing avalanches has not yet been found.
C'est comme une ceinture de sécurité dans la voiture, elle va permettre de ne pas traverser le pare-brise, mais elle ne va pas empêcher l'accident. Donc tous ces appareils sont indispensables pour avoir une chance d'être ressortis vivants, ou en tout cas retrouver les gens sous l'avalanche, mais n'ont jamais empêché une avalanche de partir.
So can we predict avalanches and know where and when they will threaten us? Today, specialists are able to hone in on high-risk zones. There are two aspects to their technique. Firstly, there's the systematic comparison of meteorological data with that of previous avalanches. If these data correspond to a similar zone, the risk is maximal. The other side to the technique involves studying snow and the form of the grains in the snowpack. Spotting the large, hard snow grains and depth hoar gives a good indication of the avalanche risk. But although studying the snowpack is very effective, it is impossible to study all snow-covered peaks that pose danger.
Chaque situation est un cas particulier, je dirais. On n'a jamais deux chutes de neige identiques dans la saison, ni même sur 20 ans.
Of course, nowadays, ski resorts are closely monitored, and they rarely fall victim to deadly avalanches. But in the mountains, zero risk doesn't exist. So what will be the situation tomorrow? Will global warming bring the end to avalanches?
Le risque d'avalanche naturelle, globalement, devrait diminuer avec le réchauffement climatique. On le comprend bien, c'est simplement parce que l'enneigement va diminuer. Cette diminution, d'ailleurs, peut être assez importante, puisque dans les projections pour la fin du siècle, elle pourrait être réduite jusqu'à 80%.
Snow melt are underway. Scientists have already confirmed it. By 2050, avalanches might be reserved for the world's highest peaks. But what is going to happen in the meantime? Since the 70s, studies have shown that aerosol avalanches, those composed of cold and dry snow, are less and less common, and therefore that the percentage of dense and humid avalanches is on the rise. We have seen that the cold causes condensation. The gas becomes a liquid, then a solid. With the heat, it's the opposite. The solid, i.e. the snow, becomes liquid in the form of water. This phenomenon is responsible for a type of avalanche that already exists, but is about to become more common during the winter. Spring avalanches.
Cette eau, qu'est-ce qu'elle va faire? Elle va couler dans le manteau neigeux et en fonction des différentes couches qu'elle atteint, elle va déstabiliser ces différentes couches.
Remember slab avalanches? When a fragile layer made up of millions of bead-like grains of snow moves the slab sitting on top of it? The difference with humid snow avalanches is that the water, which can penetrate right through to the ground, doesn't move just the slab, but the whole snowpack. These avalanches are very slow, extremely dense, and contain enormous volumes of snow.
Et potentiellement, ça peut être des phénomènes dangereux puisque c'est une neige qui est plus lourde, donc qui potentiellement pourrait provoquer davantage de dégâts.
In any case, scientists are sure that although a reduction in the amount of snow will over time limit the number of avalanches, this is not necessarily good news. This is mainly because of a little-known fact. The whiteness of the snow reflects the sun's rays, sending them back into space. Snow, therefore, helps to limit the warming of our planet. The less snow there is, the more the risk of global warming will increase. Perhaps it will even increase to the point that one day we will miss these forces of nature.